Alright, back with another video here, and still didn't grab my calculator, but that's alright. We'll make this work. So we're going to talk about z-scores. So this table right here, the positive z-scores, and the negative z-scores is the other one we're going to look at. These are found in your appendix. You can also do a Google for them. I will try to post up a PDF scanned copy of them, but I think you can find them just fine at the end of your textbook on the electronic copy as well. All right, so let's talk about how we can calculate z-scores. So let's say somebody asked you, what's the area corresponding to a z-score of, let's do negative 0.32. So let's make our distribution, graph it out. That doesn't look very good, but for z-scores, this is where the mean is 0. Negative 0.32 would be there. And if we're saying the probability, we want to find the probability of maybe less than. So if we find this z-score here, we'll go to our table. We're going to look for 0.3, and we go over to where the hundredths place says 0.02, and we'll scroll down, and you see 0.3745. That is this shaded area right here, 0.3745. So that is the probability of getting a z-score of less than negative 0.32. And if you're talking about greater than, this area then is 1 minus that value. In other words, it's equal to 0.6255. Okay? That would be this non-shaded area. So basically the area underneath the normal distribution will always be equal to 1. Now, let's say we have a couple pieces of data. We have mu is 21, and sigma is 3. In other words, the population mean is 21, the population standard deviation is 3, and we want to do the probability that the x value is greater than 14. So what we'll want to do is sketch our curve, label our mu is 21, and that's the exact middle. Now, we want to figure out where x is greater than 14. Well, x equal to 14 is right there. So that is all of this area up here, right? Greater than. So we're going above. Now we want to figure out the probability of that. So we want to figure out this area. So what we need to do is find a z-score that corresponds to that. So we have z is equal to x minus mu over sigma. So in this case, we just plug away our points. So 14 minus 21 divided by 3. So 14 minus 21 is 7 over 3 gives me, by the way, negative, and we get negative 2.33. And for z-scores, we always use 2 decimal places of accuracy. So if we go look that up now, we have negative 2.33. So 0.0099. So that is this area right here is 0.0099. Now if we want to figure out this area right here, we do 1 minus that, because the area under a probability density curve is always going to be equal to 1. So when we do that, we'll end up with 0.9901. So that is the probability of getting an x value greater than 14. So this could be anything for saying you want to pick out of a group of individuals visiting Walmart, and maybe the mean age is 21, and you want to find the probability you pick somebody greater than the age of 14. And the standard deviation is 3 years. Okay? So 2 standard deviations, right, would be 6. So anyways, those are pieces of information you might need to know. All right. Now, let's turn to another example that is in chapter 6, and it's on my slides. It is, hold on a second. Borway Heights. So in this problem. Why do doorways have heights of 6 foot 8 inches? Typical home doorway has a height of 6 foot 8 inches, in other words, 80 inches. Because men tend to be taller than women, we will consider only men as we investigate the limitations of the standard doorway height. Given that heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8, find the percentage of men who can fit through the standard doorway without bending or bumping their head. Is that percentage high enough to continue using 80 inches as the height? Will a doorway height of 80 inches be sufficient in the future? Okay, so let's take down the piece of information we have. We have mu, which is 69 inches. That's the mean. And then we have the standard deviation, which is 2.8. And what else do we have? We have 80 inches. So that's something about x, right? We're asking what percent of the population fits underneath the 80-inch doorway height. So that's where x equals 80. And this is where mu is equal to 69 inches. So basically, all of this area is what we want to find this time around. So we're going to find the probability that x is less than 80. Very similar to what we did previously here, except we're doing less than now. So we're going to be cumulative from the left, which is how the normal distribution table is read. So in this case, z is equal to 80 minus 69 over 2.8. Now, I believe after simplification, you should get 3.92. You might have to double check my math. I'm doing that from head. It's 11 over 2.8. 3, yeah. Oh, yeah. Yep. I believe that should be correct. Now, once we have that value, this is our z-score value. So that's the z-score corresponding to this. This is z equal to 3.92. Now, if we go to our distribution again, we find 3.5 and up. Uh-oh, it's really small, which basically means, note, for values of z above 3.49, use 0.9999 for the area. Use these common values for that result from interpolation. So in other words, in this case, about 0.9999 of the population will fit there. In other words, 99.99% will fit underneath the 80-inch door. Pretty cool. All right. There's a couple other examples I have in those slides that you should walk through, and I think the answers are there too. Other one I want to do is the elevator problem. So in the elevator problem, basically suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assume a worst case scenario in which all the passengers are male. What are the chances the elevator is overloaded, right? And so it won't move, or maybe it comes crashing down. More or less, it's probably not going to move. It'll override the belts. Assume male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Find the probability that one randomly selected male has a weight greater than 156.25 pounds. So probability x is greater than 156.25 pounds. That's what we're finding. We're finding that probability. So draw our distribution. Write down the stats we have, which is we have mu, which is 182.9 pounds. That's just a dash. 182.9. And the standard deviation is 40.8. Now, the z-score corresponding to this is going to be the 156.25, right? So that's where we put our x value in, the test value we want, and then minus our mu, which is 182.9, then divided by our 40.8. And once we've done that, we should get a value of negative 0.65. Now, if you look at that, right, this is a z-score. So this is where z equals 0. So we're going to be working with a z is equal to negative 0.65. And we want the probability that x is greater than, so it's going to be all that area above it. So let's go find where that is on there. And pull our table out again. Are we working on the positive side? No. We're working on the negative side. So we're at 0.65. So go to 5. We get 0.2578. That is this area right here, 0.2578. So this area here is 1 minus 0.2578. In other words, 0.7422. That is the probability that you get one randomly selected individual greater than 156.25 pounds. Now, the twist for this problem, for the elevator problem, is that what happens if we have a sample of males? So we have a sample of males. So we have 16 males have a mean weight greater than 156. So find the probability that a sample of 16 males have a mean weight greater than 156.25 pounds, which puts the total weight at 2,500 pounds, exceeding the maximum capacity. So in this example right here now, we're actually doing where we have a mean of a sample of men. So 16 is the men. So in this case, we're doing 16 men. And our variance is still going to be the same, 40.8. And our mean is 182.9, right? Now, our formula is adjusted when we're doing a sample. It's actually this piece that's going to change. It's going to be mu x, or standard deviation of x divided by the square root of n. And you'll still have x minus mu here. But it's just x bar, which is what this should be, mu of x bar. In this case, we're wanting to know the probability that the group weighs more than 156.25 pounds, and then minus the 182.9. And then in this case, we have 40.8 divided by the square root of 16. And now this will give you a different z-score value. In fact, it'll give you negative 2.61. If you were to draw your distribution, you'd see that negative 2.61 is way out here, which means the probability has gotten even bigger that the mean weight of the elevator is going to be overloaded. In fact, it's going to be so overloaded that the probability of this is 0.9955, which is pretty crazy. That basically it's 99.55% chance that the elevator is going to be overweighted. Pretty cool that you can do these kind of calculations. And I guess that's just what I want to talk about for a little bit so you guys have some more examples. Cool.